Hello, my name is Michael Prastupa, and today I'll be presenting our work analyzing neural Jacobian methods in applications of visual servoing and kinematics control. The too long didn't read of our work is Let's Learn Robotic Motion, where we are primarily interested in serial manipulators. The motion of a robot can be described with the following equation, where the velocity of the end effector is equivalent to the Jacobian with respect to the kinematics equations times the velocity of the joint angles. Unfortunately, calculating the Jacobian can be difficult in practice. This can arise in image-based visual servoing, where an analytic Jacobian term does exist, but because of dependency on depth information, which is typically approximated, this may not be an effective term to use, and more of a problem is this requirement on camera calibration. So every time the camera might become uncalibrated, your analytic Jacobian may not be accurate, and so having a way to approximate this term is valuable. The other issue is in more general robotics, where there might be uncertainty in the kinematics or the dynamics of the robotic system. An example of what we refer to here is that there might be an unknown geometry of the object held by a robot, such as the wooden spoon in the image here. And here we might have the end effector location defined as the tip of the wooden spoon, but because we don't know anything about this object, we can't derive a closed form analytic Jacobian term, and so we need a way to approximate it instead. So the fundamental research question of this work is, how can we approximate the Jacobian? There's been lots of previous work on this topic, particularly in visual servoing, where authors have proposed local approximation methods, such as using finite differences or updating these finite differences with a Breudian update, but unfortunately these immediate finite approximations only work in a portion of the workspace and do not work across the full workspace, particularly as you move further away from the point the approximation is taken. Other approaches include global approximation methods through multiple local linear fits using a k-nearest neighbors approach, but unfortunately the issue with these methods is that there's a high memory cost, as you need to hold on to all of the interactions in the robotic system because the k-nearest neighbors is non-parametric, and there's an expensive online computation fitting the local linear Jacobian at every step, particularly as you need a large number of neighbors to get a competitive approximation. Our proposed solution is, let's consider function approximators instead, focusing particularly on neural networks. The nice thing about neural networks is they're parametric, so computation is proportional to the model size. It's a sort of global method, as we can get a Jacobian approximation across the full workspace, and theoretically, there's a lot of work on neural networks suggesting that if you were given a sufficient amount of training data and a sufficiently large neural network, we could hypothetically recover the ground truth underlying function. And now I'm going to talk about our methodologies, which include the neural Jacobian method and the neural kinematic method. The neural Jacobian method directly predicts the Jacobian and is trained by applying the secant assumption, which says that for finite differences between end effector locations, this is approximately again equal to our Jacobian term, which we're going to learn, times the finite differences of the corresponding joint angles for those end effector locations. And so xi, xj, qi, qj are just poses of the robot, basically, and what the differences between them. And here the secant constraint is just saying, well, for two nearby points, we can draw a straight line between them, which is what the approximation is saying. So the objective function minimize in the neural Jacobian method says, let's minimize the secant relationship between the k-nearest neighbors of some desired training example, q's angles. And so we have two terms to this loss function. The first is minimizing our robotic equations in measurement space. So we're trying to make, both sides of the previous equation as equal to each other as possible over some neighborhood around our current training example. And the second one says, let's minimize the same relationship in motor space. So we take our prediction, invert it, and then try to minimize it on the inverse relationship that way. And this is not always going to help, as our experiments will show, but the idea of why we thought to try it is because, well, sometimes the other issue with Jacobians is that they can have singularities, and so if we try to encourage the network to always allow invertibility, maybe we can, although hurt our approximations, kind of mitigate the adverse effects of singularities in that way, although that was just a thought. So in order to train this neural Jacobian idea, we collect data, which are just interactions of the joint angles and the end effector locations of the robot moving around. We then define the k-nearest neighbors in our training set for some current training example Q, and then we just take mini batch updates over this neighborhood as discussed. And something in our experiment which is of note is that roughly over here we have some betas which beta is a weighting term. When beta is equal to 0, we do not minimize the motor space relationship, and when beta is equal to 1, we include minimizing in the motor space relationship. So once we've trained this neural Jacobian approach, we just have to do forward passes in our neural network to recover the Jacobian. So we pass our joint angles Q through the network, and it'll directly give us the Jacobian approximation based on how we trained it. Our second approach is called the neural kinematics approach, where instead what we do is we train a neural network to predict the forward relationship, so the kinematics, for example. So the outputs of our network here are trying to mimic the end-effector locations of the robotic system. So utilizing backpropagation from these forward predictions, we then just differentiate with respect to each output, and this is going to give us the Jacobian term. And so why we thought this might work is that neural network theory seems to suggest that when a network is trained to predict a function, it also learns to recover the derivative functions as well. And so kind of the underlying question is, how well does this happen in practice for robotic problems? And so here's a simple 1D example of what I'm talking about. The neural network, which is the blue line, was trained to predict the sine function here. And using this backpropagation from the output to the inputs, we see that the neural network also was able to approximately recover the derivative function of sine, which is the cosine. So it only saw the green line during training, and it successfully seemed to recover the orange line without being trained to do so. So at deployment time, here's roughly what happens in the neural kinematics approach. Given the joint angles, the neural network processes this, gives us some prediction of the approximate end-effector location, and then we backpropagate from the outputs of this all the way through our joint angles Q, and this is how we get the Jacobian term. So those are our methods. Now let's talk about what experiments we did to validate the efficacy of these two proposed methods. So we had 3 questions we were interested in answering. Can we use the Jacobians in existing control law? Here we use inverse Jacobian control. How can we determine the accuracy and effectiveness of our Jacobians? And does any of this actually work on a real robot system? And here is just the control law that we used in our experiments. We did not include this term, which is to help against singularities as I understand it, only focusing on this portion during our experiments, which is just take the pseudo-inverse of our J and multiply it by the target position that we want to go to in our current one and send that as the joint velocity command. So this is joint velocity command sent to the robot, and that's how we get it to move. So here's our kinematic simulator of how we conducted our experiments, where the orange dots here are these X's that we've been talking about, and we want to align them with the blue dots down here, and these are the target points. So we want these 4 points to perfectly align with the blue points here, and that's what we did in simulation. We considered 2 setups, a single point case with 3 features and a multi-point case for 12 features. Here, features are defined as the x, y, z locations of points. So in the single point, 1 point, 3 features, x, y, z. 4 points, 12 features, x, y, z for each of the 4 points. So here's our Kinova Gen-3 light experiments, which included the visual servoing that's in this diagram, and also a kinematic setup where the features are similarly defined. It's 2 features because x, y plane of the image, and the kinematic 3 features, similar setup, x, y, z in the robot's coordinate space. And here we have the tracked point of what we are trying to match up with this target position. So now I'm going to present some video footage of our robotic experiments, where here I have the kinematic simulator, which we replayed the trajectories that were ran on the robot or produced by the robot more accurately. And the orange boxes show roughly where the targets are supposed to be. So let's see how that looks in practice. So as we see, the robot is moving towards the target, swings out just a little bit, but it successfully seems to reach the blue dot here, which is what we hope to see. And so let's replay it again. So as the robot moves, it's moving towards this blue dot, not the red dot. The target's roughly somewhere around here, and the simulator just helps us give a clear target of where that is, and our neural kinematics approach was able to successfully move towards that target. Next, let's take a look at our neural Jacobian method, which on the same target, it's going to fail to reach it, but the setup is basically the same thing, where we have our target roughly defined here. Here's what it actually is if you take a look at the simulator. And so let's take a look at that failure case now. So here we see our neural Jacobian method. It's getting close, but unfortunately, for some reason around this point, the approximations broke down, and we see that it's starting to diverge, and it converges to the wrong point. Here I'm going to show just a single time our visual servoing experiments, where the 3 red boxes are our methods that we were running experiments to evaluate, and the blue is our baseline. So the idea is, again, that we have the tip of the robot defined in the image, which is tracked here, and we want to move it towards the green dots in our experiments. So when I play the video here, we can see that all our methods, baseline included, do successfully seem to get close to the target. Although the trajectories and speeds vary between the methods, we do see that our baseline and our methods are successfully able to reach the target. And so it's just showing that our methods do in fact work on the robot. So let's take a look at our experimental results now. Here is our table from our paper, which is the percentage of successful reaches based on some threshold criteria in the allotted time that we gave each trajectory over increasing distances. Something important to note is TJ at the bottom is for using the true Jacobian, and the control law that we use is only guaranteed to be locally convergent, and as you can see that even the true Jacobian doesn't always successfully work. The next notable thing in our single point case is that all our neural methods compare comparably in this under-constrained setting, although the neural Jacobian methods are slightly inferior to our neural kinematics approaches. And something interesting that we found is that, we talked about how the bidirectional neural Jacobian may not always be beneficial, which does seem to happen in the single point case when compared to the neural Jacobian without this bidirectional fitting. But when we move to the more complicated multi-point case, we actually end up finding a performance improvement over the neural Jacobian method. So this might suggest that our bidirectional fitting is more useful when there are more output features than degrees of freedom to move the robot. Next, let's talk about how one of our experiments to analyze the Jacobian. We have more results in our paper, and so we focus on this one, which was trying to separate trajectories in the single point simulator scenario based on Lyapunov theory, which basically says if the true Jacobian times its inverse is always positive definite, you're guaranteed to be locally convergent. And so what we did for this experiment was taking the true Jacobian multiplied by the approximated Jacobian hat from our different methods. How well did they perform? When we take a look at our neural kinematics approaches, we find that the choice of activation functions seem to make a notable difference in whether or not the trajectories would always produce Jacobians that were always positive definite. So TANH seems to give a much better positive definite performance than the Rayleigh activation function. And when we look at our bidirectional fitting compared to the neural Jacobian, we found that indeed there is a little bit of improvement in terms of finding, approximate pseudo-inverses that lead to always being positive definite. But as we previously talked about, this may not actually be necessarily beneficial in terms of actually doing control. So those are some of our experiment results, and there's more in our paper. And so in conclusion, we found that our methods could work as good as baseline. And we got a 50% improvement with a bidirectional neural Jacobian and 20% in the neural kinematics approach over our best approximation baselines. We found that our approximations can typically be more accurate and give some nice properties over alternative baselines that we considered. And we found that our methods were applicable on real robotic systems. So for future work, some ideas we had were, looking at singularity configurations and seeing how approximations compare to that. We also thought that it might be interesting to explore more complex kinematic settings such as robotic fingers, where there is this ambiguity for Jacobians. And we also figured there might be more work to be done in visual servoing, where more specific domain problems such as tracking error could adversely affect our performance. And so at this point, I reiterate what I mentioned on the previous slides or conclusions in future works. My name is Michael Prastupa again, and here's an email to contact me, and we release our code for anyone interested. Thank you.